Welcome! In this session, we'll dive into solving the problem number 1382, balance a binary search tree. This involves transforming an unbalanced binary search tree into a height-balanced one while maintaining its in-order traversal property. Let's explore the approaches and techniques to tackle this problem effectively. In this problem, we are given the root of a binary search tree, or BST, and our goal is to return a balanced version of this tree. The new tree must contain the exact same node values as the original tree, and if there is more than one valid way to balance it, we can return any of those valid results. A balanced binary search tree is defined as a tree where, for every node, the depth of its left and right subtrees differs by no more than 1. The input to the problem is the root node, represented using the standard tree node structure. This structure includes an integer value for each node, along with pointers to its left and right child nodes. The output is a tree node object that represents the root of the balanced BST. The tree must satisfy the BST property and meet the height-balanced criteria. Let's look at the first example. The input tree is represented as root equals 1, null, 2, null, 3, null, 4, which translates to a degenerate or skewed binary search tree. In this tree, all nodes form a straight line, with each node having only a right child. Visually, the tree looks like this. The root node is 1, which points to 2, then 2 points to 3, and finally, 3 points to 4. The output for this input is 2, 1, 3, null, 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 4, which represents a more balanced tree. One possible balanced tree for the first example is shown here. In this tree, the root is now 2, and it has two subtrees. The left subtree contains the node 1, and the right subtree contains the node 3, which itself has a right child. This tree is balanced because the depth difference between the left and right subtrees of every node is at most 1. The input tree, being a single line, was unbalanced, but now the output tree satisfies the height-balanced property while maintaining the BST structure. For instance, all nodes in the left subtree of 2 are less than 2, and all nodes in the right subtree are greater. Now, let's consider another example. In the second example, the input tree is represented as root equals 2, 1, 3. This time, the tree is already balanced. The root node is 2, with 1 as its left child and 3 as its right child. The output for this case is the same as the input, 2, 1, 3. The tree remains unchanged because it already satisfies the conditions of a balanced binary search tree. The depth difference between the left and right subtrees of all nodes is 0, which is within the allowed limit of 1. Therefore, no rebalancing is needed. Now, for the third example, the input tree is represented as root equals 3, 1, 4, null, 2. The visual representation of the tree shows that the root is 3, with 1 as its left child and 4 as its right child. Additionally, the node 1 has a right child, which is 2. This input tree is not balanced because the left subtree of the root is deeper than the right. Specifically, the left subtree's depth is 2, while the right subtree's depth is 1. A balanced version of this tree is returned as 3, 2, 4, 1. In the balanced version of the third example, the root remains 3, but the left subtree is now structured differently. The node 2 becomes the left child of 3, and 1 becomes the left child of 2. The right subtree of 3 still contains the node 4. This rearrangement ensures that the depth difference between the left and right subtrees of every node is at most 1. The balanced output tree maintains the BST property, where all nodes in the left subtree are less than the root, and all nodes in the right subtree are greater. The constraints for this problem allow up to 10,000 nodes, and node values range from 0 to 100,000. Special cases to consider include single-node trees, already balanced trees, and highly skewed trees, all of which must be handled correctly to produce a balanced BST as output. To solve the problem of balancing a binary search tree, the goal is to transform the given BST into a height-balanced BST while maintaining the in-order property of binary search trees. Let's first consider a brute force approach. This method involves performing an in-order traversal of the tree, which retrieves all the node values in sorted order into an array. Once we have this sorted array, we can recursively reconstruct a balanced BST by choosing the middle element of the array as the root. The left half of the array becomes the left subtree, and the right half becomes the right subtree. The key observation here is that an in-order traversal of a BST always produces a sorted list, which makes this approach very intuitive. In terms of complexity, it requires O(n) time for the traversal and another O(n) for reconstructing the tree, resulting in an overall time complexity of O(n). However, we must also account for the O(n) space used to store the array, which is an important trade-off to remember. While the brute force approach is simple and intuitive, it requires additional space to store the sorted array, which might not be ideal in memory-constrained situations. To address this, an optimized approach aims to rebalance the tree in place without creating an auxiliary array. This more advanced method uses rotations, such as left and right rotations, to directly modify the tree structure and balance unbalanced subtrees. The key advantage here is that it avoids the memory overhead of storing a sorted array. However, this approach introduces significant complexity, as rebalancing the tree requires careful handling of rotations to preserve the binary search tree property. From a complexity perspective, the time complexity increases to O(n) log n due to the iterative rebalancing of subtrees, and the space complexity becomes O(h), where h is the height of the tree, as recursion is used to traverse the tree. The in-place optimization approach may save space but comes with its own set of challenges. Implementing rotations to balance subtrees can be tricky, and the multiple passes required for rebalancing introduce runtime overhead. For this reason, we opted to use the first approach, reconstructing the tree using a sorted array, as our final strategy. By leveraging an in-order traversal to produce a sorted array, we ensure a straightforward and reliable process for creating a balanced BST. This method is conceptually simple, easy to implement, and avoids the potential pitfalls of manual rotations. While it does require O(n) space for the array, this trade-off is acceptable given modern memory constraints, and it ensures that the input tree remains unmodified. The simplicity and efficiency of this approach make it a strong choice for solving this problem, especially when working with large trees. The key insight that underpins this solution is the realization that an in-order traversal of a binary search tree produces a sorted array. This insight allows us to bypass the complexities of rebalancing logic and instead focus on constructing a balanced tree directly from the array. By selecting the middle element of the sorted array as the root and recursively building subtrees, we achieve both balance and correctness. The final complexity of this approach is O(n) for time, thanks to the linear traversal and reconstruction, and O(n) for space due to the array. This balance of simplicity, efficiency, and maintainability is what makes this strategy the most practical and effective solution for balancing a binary search tree. To solve the problem of balancing a binary search tree, we follow a brute force approach that involves reconstructing the tree using an in-order traversal. This method ensures that the resulting tree is both height balanced and maintains the sorted order of elements, which is a fundamental property of binary search trees. The first step in this process is performing an in-order traversal. The goal here is to extract all the elements from the tree into a sorted list. We begin at the root node and recursively visit the left subtree. Once we've explored the left side, we record the value of the current node and append it to our list. Then, we traverse the right subtree in the same recursive manner. The result is a sorted list of all node values because the in-order traversal of a BST naturally visits nodes in ascending order, thanks to the property that all left descendants are smaller than the root, and all right descendants are larger. This sorted list becomes the foundation for constructing a balanced tree in the next step. After obtaining the sorted list, the next step is to reconstruct the tree in a way that ensures it is height balanced. To achieve this, we select the middle element of the list to serve as the root node. This choice guarantees that the left and right subtrees will be roughly equal in size, which is critical for balancing. We then recursively apply the same process to the left half of the list to construct the left subtree and to the right half of the list for the right subtree. Once these recursive calls are complete, we return the root node of the newly constructed tree. This approach works because selecting the middle element minimizes the height of the tree at each step, and dividing the list in half ensures that the subtrees remain balanced at every level. Additionally, we account for edge cases such as an empty tree, where we simply return null, or a tree with only one node, where no reconstruction is needed. If the tree contains duplicate values, we handle them consistently, for example, by placing all duplicates in the left or right subtree. The key insight here is that by dividing the list at its midpoint, we naturally satisfy the balancing criterion. The height difference between the left and right subtrees of any node remains at most 1. This algorithm is efficient because both major steps, performing the in-order traversal and reconstructing the tree, operate in O(n) time, where n is the number of nodes in the tree. The traversal step gathers all the elements into a sorted list, and the reconstruction step processes each node exactly once during the recursive calls. This makes the overall time complexity linear with respect to the number of nodes. Additionally, the recursive nature of the algorithm simplifies the logic for both traversal and subtree construction, as each operation naturally follows the recursive structure of the tree. Using a sorted list as an intermediate data structure ensures correctness during reconstruction, as it allows direct access to the middle element, which is required to maintain balance. The primary data structures involved are an array or list to store the sorted elements and the tree node structure, which represents the nodes of the tree. The two key operations are in-order traversal, which involves visiting nodes in the left root right order, and tree reconstruction, where the list is divided recursively to create balanced subtrees. Both of these operations contribute to the overall efficiency and correctness of the algorithm. The reconstruction step also has a linear time complexity, as each node is processed exactly once, ensuring that the algorithm remains efficient. To optimize further, we can avoid unnecessary memory usage by reusing the input tree nodes during reconstruction instead of creating new ones. Additionally, while the algorithm is naturally recursive, we could use an iterative approach for the in-order traversal to reduce recursion overhead, especially for very large trees. Let's look at an example to see how this process works in practice. Consider the input tree where the root is 10, with left and right subtrees containing nodes 5 and 20, respectively. The left subtree of 5 contains nodes 1 and 8, while the right subtree of 20 has a single node, 25. Performing an in-order traversal on this tree results in the sorted list 1, 5, 8, 10, 20, 25. This list will now serve as the input for the reconstruction step. Using the sorted list, we reconstruct the tree by first selecting the middle element, 10, as the root. The left half of the list, 1, 5, 8, is used to construct the left subtree, where 5 becomes the root. The left child of 5 is 1, and the right child is 8. Similarly, the right half of the list, 20, 25, is used to construct the right subtree, where 20 becomes the root. The left child of 20 is null, and the right child is 25. The final output tree is height balanced, with 10 as the root, 5 and 20 as its children, and the remaining nodes distributed evenly across the left and right subtrees. This restructuring ensures that the height difference between the left and right subtrees of any node is at most 1, satisfying the balancing criterion while preserving the binary search tree property. This solution to LeetCode problem number 1382, balance a binary search tree, focuses on reconstructing the tree to ensure it is height balanced. The first part of the code defines a helper function in_order_traversal, which collects all the node values of the binary search tree, BST, in sorted order via an in-order traversal. This traversal visits nodes in the left subtree, the current node, and then the right subtree recursively, ensuring the results are in ascending order. The second part of the solution defines another helper function build_balanced_tree. This function takes the sorted values obtained from the in-order traversal and recursively constructs a balanced BST. The middle element of the current range is chosen as the root to ensure the tree remains height balanced. The function then recursively builds the left and right subtrees using the elements before and after the middle index, respectively. The main function balance_BST integrates these two helper functions. It first calls in_order_traversal to retrieve the sorted values from the input BST. Then, it uses build_balanced_tree to construct and return the balanced BST from the sorted values. This approach guarantees that the resulting tree is height balanced while maintaining the BST properties. The algorithm has a time complexity of O(n), where n is the number of nodes, as both the in-order traversal and the tree reconstruction involve visiting each node once. The space complexity is O(n), due to the storage requirements of the sorted list and the recursion stack during tree reconstruction. Overall, this solution is efficient, concise, and adheres to the problem's constraints and requirements. Here, we start implementing the solution for balancing a binary search tree in Java. First, we define the treenode class to represent the structure of a binary tree node, which has an integer value and pointers to its left and right child nodes. Then, in the solution class, we define the balance BST method, which is the main method for solving the problem. The approach starts with an in-order traversal of the input tree, which will give us the node values in sorted order. To store these values, we use an array list called sorted values. The in-order traversal method is a helper function that we call recursively to visit the nodes in the correct order. This ensures that all the values from the left subtree are processed first, followed by the root, and then the right subtree. After completing the traversal, the next step is to use these sorted values to reconstruct a balanced binary search tree, which will be handled by another helper method called buildBalanceTree. The in-order traversal method continues by checking if the current node is null. If it is, the function simply returns, as there is nothing to process. Otherwise, we recursively traverse the left subtree, add the value of the current node to the sorted values list, and then traverse the right subtree. This ensures that all values are collected in sorted order. Next, we move to the buildBalanceTree method. This function takes the sorted values and uses a divide and conquer strategy to construct a balanced binary search tree. We calculate the middle index of the current range, create a new tree node using the value at this index, and recursively build the left and right subtrees using the left and right halves of the list, respectively. If the start index exceeds the end index, we return null to indicate that there are no nodes to add in that range. This recursive process ensures that the tree remains height balanced as we build it from the sorted values. Here, we start by analyzing a simple binary search tree where the root is 2, and it has 2 children, 1 on the left and 3 on the right. This tree is already balanced, but we will still follow the algorithm to confirm. The first step is to perform an in-order traversal. We begin at the root, traverse the left subtree to visit node 1, and add 1 to our sorted list. Next, we visit the root itself, adding 2 to the list. Finally, we traverse the right subtree to visit node 3, adding 3 to the sorted list. The result of this traversal is a sorted array 1, 2, 3. Using this sorted array, we rebuild the tree to ensure it's balanced. The midpoint of the array is 2, which becomes the root of the balanced tree. The left subtree is constructed using the values before the midpoint, creating node 1. This completes the left side of the tree. For the right subtree, we use the values after the midpoint, which is just the value 3. This creates node 3 as the right child of the root. The output is a balanced binary search tree that looks exactly like the input, 2 as the root, with 1 on the left and 3 on the right. Now, moving on to a less balanced example, we have a skewed binary search tree. Here, the root is 1, with a right child of 2, and another right child of 3. This tree is unbalanced because all nodes are aligned to the right, making it essentially a linked list. To balance this skewed tree, we start with an in-order traversal. Since there is no left subtree, we directly visit the root, 1, and add it to the sorted list. Then, we traverse to the right child, 2, adding it to the list, and continue to the next right child, 3, adding that as well. The result is a sorted array 1, 2, 3. Using this sorted array, we rebuild the tree. The midpoint, 2, becomes the new root. For the left subtree, we use the values before the midpoint, which is just 1. This creates node 1 as the left child of the root. For the right subtree, we use the values after the midpoint, which is just 3, creating node 3 as the right child of the root. The output is a balanced binary search tree with 2 as the root, 1 as the left child, and 3 as the right child. Now, let's look at a larger, unbalanced binary search tree. Here, the root is 8, with 4 and 10 as its children. Node 4 has its own children, 2 and 6, and node 10 has a single right child, 20. This tree is unbalanced because the right subtree of node 10 is deeper than the left subtree. To balance it, we start with an in-order traversal. We traverse the left subtree of 8, visiting nodes 2, 4, and 6, which we add to the sorted list in this order. Then, we visit the root, 8, adding it to the list. Finally, we traverse the right subtree of 8, visiting nodes 10 and 20, and add them to the list. The result is a sorted array 2, 4, 6, 8, 10, 20. Using this sorted array, we rebuild the tree. The midpoint, 8, becomes the new root. For the left subtree, we use the values before the midpoint, 2, 4, 6, the midpoint of this subarray, 4, becomes the left child of the root. Then, the values before 4, which is just 2, create node 2 as the left child of 4. The values after 4, which is just 6, create node 6 as the right child of 4. For the right subtree of the root, we use the values after the midpoint, 10, 20. The midpoint of this subarray, 10, becomes the right child of the root. Finally, the value after 10, which is 20, creates node 20 as the right child of 10. The output is a balanced binary search tree with 8 at the root, 4 and 10 as its children, and their respective subtrees balanced. This completes the process of balancing the tree. The time complexity of this solution involves two primary steps: performing an in-order traversal to flatten the binary search tree into a sorted list and then reconstructing a balanced binary search tree from that list. Let's break this down. First, during the in-order traversal, we visit each node of the tree exactly once. For a tree with n nodes, this takes n time. Each recursive call processes one node at a time, and since each operation during traversal is constant time, the total time adds up to n. Next, when we build the balanced tree, the build_balanced_tree function uses a divide and conquer approach. By selecting the middle element of the sorted list as the root and recursively building the left and right subtrees, the entire list is divided into two halves at each recursive step. This ensures that every node is processed exactly once, which also results in n time. Combining these two steps, the overall time complexity of the algorithm is n plus n, which simplifies to n. Now, let's analyze the space complexity, which comes from two main components. First, the recursive call stack used during the in-order traversal. In the worst-case scenario, if the tree is completely unbalanced, such as a skewed tree, the recursion stack depth can reach n. On the other hand, for a perfectly balanced tree, the depth of the recursion stack would only be log n. The second component is the additional space needed to store the values of all nodes in the sorted list. The in_order_traversal function creates an array of size n, which requires n space. Lastly, the recursive call stack for build_balanced_tree also contributes to the space complexity. Here, the depth of recursion depends on the height of the tree being built. For a perfectly balanced tree, the recursion depth is log n. When combining these factors, the storage of the sorted list dominates, so the overall space complexity is n. Combining the space components, we get n for the sorted list and, in the worst case, log n for the recursion stack during tree reconstruction. Together, this results in a total space complexity of n plus log n, which simplifies to n. Now, let's compare this approach to a brute force method. A naive solution might involve repeatedly inserting nodes into a new tree to maintain balance. This would require n log n time, as each insertion into a balanced tree takes log n, and we'd repeat this for n nodes. However, the current solution avoids this overhead by leveraging the sorted property of the in-order traversal and constructing the tree in linear time. Whether the tree is already balanced or completely unbalanced, the time complexity remains n, and the space complexity is dominated by the n storage for the sorted list in recursion. To mathematically prove the big O complexity, consider the two main operations. First, the in-order traversal processes each of the n nodes exactly once, making its time complexity directly proportional to the number of nodes, n. Second, the tree reconstruction step also processes each node once to create a new node. The divide and conquer nature of this step ensures that no node is processed more than once, resulting in n time. For space, the sorted list requires n memory, and the recursion stacks for both traversal and reconstruction together contribute log n in the best case and n in the worst case. Since the sorted list dominates, the overall space complexity is n. These components together confirm that the solution has an overall time complexity of n and a space complexity of n. When rebalancing a binary search tree, there are several common mistakes to watch out for. First, it's crucial to preserve the in-order property of the BST. This means the nodes must remain sorted when you traverse the tree in order. Rearranging nodes arbitrarily can violate this property, leading to an invalid BST. Next, edge cases like empty trees, single-node trees, or highly skewed trees often get overlooked. These scenarios need special handling to ensure your solution is robust. Additionally, if the BST allows duplicate values, you must address how duplicates are placed. For example, Consistently placing duplicates on either the left or right subtree is critical to maintaining balance and correctness. Another common pitfall is using inefficient balancing methods. Avoid trying to directly rebalance the tree without first leveraging an in-order traversal, as this can introduce unnecessary complexity. Lastly, recursive calls can be tricky. Miscalculating the midpoint or mishandling indices for the left and right subtrees can cause infinite recursion or an incorrect tree structure. Always double-check your base cases and index logic to avoid these issues. Now, let's talk about insights that can help during interviews. Recognizing patterns is essential. Tree problems like balancing, traversals, or reorganization often benefit from a divide-and-conquer approach. Understanding how to apply in-order traversal is particularly valuable here. Additionally, interviewers commonly focus on time complexity. The optimal solution for balancing a BST runs in O(n) time, as both in-order traversal and tree reconstruction take linear time. It's important to communicate the trade-offs in your approach as well. While the most efficient solutions use O(n) time and space, iterative or in-place solutions might optimize space at the cost of clarity. Be ready to explain why you chose a certain approach and how it aligns with the problem's constraints. Lastly, don't forget to address edge cases explicitly in your explanation. Demonstrating that you've considered various scenarios shows interviewers your thoroughness and attention to detail. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 108, which involves converting a sorted array into a height-balanced BST, shares similar concepts of tree reconstruction. Of course, LeetCode 1382, the problem we're discussing, focuses specifically on balancing an existing unbalanced BST. Another useful problem is LeetCode 230, which involves finding the kth smallest element in a BST. It highlights the importance of in-order traversal for working with ordered data in BSTs. Finally, LeetCode 98 asks you to validate whether a given tree is a valid BST. This reinforces your understanding of BST properties, which are essential when rebalancing or reconstructing a tree. Finally, let's consider alternative approaches and their trade-offs. The most common method involves performing an in-order traversal to extract the nodes into a sorted array, which takes O(n) time. You then reconstruct the tree recursively from this array, again in O(n) time. This approach is simple and efficient but requires O(n) space for the array. For more advanced users, in-place balancing techniques aim to avoid creating a separate array. These methods are space-efficient, using only O log n space for the recursion stack, but they come with greater implementation complexity and debugging challenges. Iterative solutions are another option, replacing recursion with an iterative approach to rebuild the tree. While this saves stack space, it can be harder to write and understand under time constraints. Lastly, instead of directly balancing the tree, you might consider converting it into a self-balancing tree like an AVL or red-black tree. While these structures handle balancing automatically, they're less common in interviews and are typically mentioned for completeness rather than practical implementation. Great job completing the problem. To summarize, we used in-order traversal to rebalance the BST efficiently. This is an important foundational concept for working with trees in competitive programming and real-world applications. Thank you for watching, and stay tuned for more exciting problems and solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!